IFR training videos, by
Toga thrust.
ADF approach. Agenda. Introduction. System description. Approach chart description. Approach follow-up. Failures and contingencies.
Introduction.
We are facing major changes in aviation, mainly in instrument flying. With the growing importance of satellite positioning, old-fashioned navigation and approach techniques will soon become obsolete. What about pilot core competencies? Are we bound to follow the line and nothing more, or should we keep training those procedures and techniques to keep what makes a pilot, mastering? You think right if you are watching this video. Let's train as a pilot. Satellite navigation and approach techniques will be a part of your training.
Theory.
System description. Automatic direction finding, ADF, is an electronic aid to navigation that identifies the relative bearing of an aircraft from a radio beacon transmitting in the MF or LF bandwidth, such as a non-directional beacon or commercial radio broadcast station. Essentially, ADF consists of a loop aerial which is rotated physically or electronically and detects the direction of minimum reception from the beacon relative to the aircraft direction. This information can be used directly to home to the beacon. Alternatively, the aircraft equipment combines the relative bearing with heading information from the aircraft compass to provide bearing position lines which may be plotted on a chart. An automatic direction finder, ADF, is a marine or aircraft radio navigation instrument that automatically and continuously displays the relative bearing from the ship or aircraft to a suitable radio station. ADF receivers are normally tuned to aviation or marine NDBs, non-directional beacon, operating in the LW band between 190 to 535 kHz. Like RDF, radio direction finder, units, most ADF receivers can also receive medium-wave, AM, broadcast stations, though these are less reliable for navigational purposes. The operator tunes the ADF receiver to the correct frequency and verifies the identity of the beacon by listening to the Morse code signal transmitted by the NDB. On marine ADF receivers, the motorized ferrite bar antenna atop the unit, or remotely mounted on the masthead, would rotate and lock when reaching the null of the desired station. A center line on the antenna unit moving atop a compass rose indicated in degrees the bearing of the station. On aviation ADFs, the unit automatically moves a compass-like pointer, RMI, to show the direction of the beacon. The pilot may use this pointer to home directly towards the beacon, or may also use the magnetic compass and calculate the direction from the beacon, the radial, at which their aircraft is located. Unlike the RDF, the ADF operates without direct intervention, and continuously displays the direction of the tuned beacon. Initially, all ADF receivers, both marine and aircraft versions, contained a rotating loop or ferrite loop stick aerial driven by a motor which was controlled by the receiver. Like the RDF, a sense antenna verified the correct direction from its 180-degree opposite. More modern aviation ADFs contain a small array of fixed aerials and use electronic sensors to deduce the direction using the strength and phase of the signals from each aerial. The electronic sensors listen for the trough that occurs when the antenna is at right angles to the signal, and provide the heading to the station using a direction indicator. In flight, the ADF's RMI or direction indicator will always point to the broadcast station regardless of aircraft heading. Dip error is introduced, however, when the aircraft is in a banked attitude, as the needle dips down in the direction of the turn. This is the result of the loop itself banking with the aircraft and therefore being at a different angle to the beacon. For ease of visualization, it can be useful to consider a 90 degrees banked turn, with the wings vertical. The bearing of the beacon as seen from the ADF aerial will now be unrelated to the direction of the aircraft to the beacon. Dip error is sometimes wrongly confused with quadrantal error, which is the result of radio waves being bounced and re-radiated by the airframe. Quadrantal error does not affect signals from straight ahead or behind, nor on the wingtips. The further from these cardinal points and the closer to the quadrantal points, i.e. 45 degrees, 135 degrees, 225 degrees and 315 degrees from the nose, the greater the effect, but quadrantal error is normally much less than dip error, which is always present when the aircraft is banked. ADF receivers can be used to determine current position, track inbound and outbound flight path, and intercept a desired bearing. These procedures are also used to execute holding patterns and non-precision instrument approaches. ADF indicators. An ADF indicator with a fixed azimuth dial. The airplane is flying a 40 degrees magnetic heading, while the station is 310 degrees relative to the plane, called relative bearing. The magnetic bearing to the station in this case is 350 degrees. The ADF indicators are a kind of navigational display consisting of a dial and a needle that rotates around the dial and points to the beacon. This needle suggests the bearing of the beacon, and to fly the from bearing, 180 degrees needs to be added or subtracted from the reading. There are two types of ADF indicators: the fixed azimuth dial type with 0 degrees always represents the aircraft nose, and 180 degrees always represents the aircraft tail, and the type with rotating dials that can be rotated to align the azimuth with the aircraft heading. Station passage. As an aircraft nears an NDB station, the ADF becomes increasingly sensitive. Small lateral deviations result in large deflections of the needle, which sometimes shows erratic left/right oscillations. Ideally, as the aircraft overflies the beacon, the needle swings rapidly from directly ahead to directly behind. This indicates station passage and provides an accurate position fix for the navigator. Less accurate station passage, passing slightly to one side or another, is shown by slower, but still rapid, swinging of the needle. The time interval from the first indications of station proximity to positive station passage varies with altitude, a few moments at low levels to several minutes at high altitude. Homing. The ADF may be used to home in on a station. Homing is flying the aircraft on the heading required to keep the needle pointing directly to the 0 degrees, straight ahead, position. To home into a station, tune the station, identify the Morse code signal, then turn the aircraft to bring the ADF azimuth needle to the 0 degrees position. Turn to keep the ADF heading indicator pointing directly ahead. Homing is regarded as poor piloting technique because the aircraft may be blown significantly or dangerously off course by a crosswind and will have to fly further and for longer than the direct track. Tracking. The ADF may also be used to track a desired course using an ADF and allowing for winds aloft, winds which may blow the aircraft off course. Good pilotage technique has the pilot calculate a correction angle that exactly balances the expected crosswind. As the flight progresses, the pilot monitors the direction to or from the NDB using the ADF, adjusts the correction as required. A direct track will yield the shortest distance and time to the ADF location. Radiomagnetic indicator, RMI. A radiomagnetic indicator, RMI, is an alternate ADF display providing more information than a standard ADF. While the ADF shows relative angle of the transmitter with respect to the aircraft, an RMI display incorporates a compass card, actuated by the aircraft's compass system, and permits the operator to read the magnetic bearing to or from the transmitting station, without resorting to arithmetic. Most RMIs incorporate two-direction needles. Often one needle, the thicker, double-barred needle, is connected to an ADF and the other, generally thin or single-barred, is connected to a VOR. Some models allow the operator to select which needle is connected to each navigation radio. There is great variation between models, and the operator must take care that their selection displays information from the appropriate ADF and VOR. This instrument display can replace a magnetic compass display in the instrument panel, but not necessarily the gyroscopic heading indicator. ADF approach chart description.
The way to get started is to quit talking and begin doing.
To have the complete description of the Jepson approach chart, please refer to the presentation. IFR training videos. By
Toga thrust.
Approach chart description.
ADF approach follow-up step by step.
Consider an NDB approach chart, LFAV. We will depict all the approach phases step by step. This part of the procedure at LFAV is not an holding pattern, it is called a racetrack. Racetracks are flight paths specified on approach charts and are used to position the aircraft on the approach track. Holding patterns are used to make an aircraft wait before approach. A racetrack is meant to be an obligatory step of the approach, or to allow for a correct preparation of the approach if not ready when reaching the fix. While it is not always mandatory to be flown, in this case, it is as it includes a step down from 2,000 feet to 1,500 feet. The outbound leg of a racetrack may be more than 1 minute or be referenced to a DME reading, or to a crossing radial. The initial approach fix is Victor Sierra NDB, frequency 317. Whatever the direction you are coming from to overfly the initial approach fix, you will enter the racetrack. You can cross-check the position of Victor Sierra by using the radial 046 degrees of the Cambrai, Charlie Mike Bravo, VOR. Until now, our minimum altitude is minimum 2,000 feet. No descent is allowed until turning inbound to the initial approach fix in the last turn of the racetrack. What if I'm not ready for the approach? You can always tell the ATC that you make another turn in the racetrack to be ready for the approach, then you are making and holding using the racetrack. You perform the entry in the racetrack exactly in the same way as for an holding pattern. In this particular case, the outbound is 1 minute, so the same as for an holding pattern. Refer to the briefing dedicated to holding patterns. Then you turn inbound to the final approach fix, which is the same as the initial approach fix in this case. When established inbound, descent rapidly to 1,500 feet. Why rapidly? Because you have to descend 500 feet and you have 2 nautical miles, so about 1 minute to descend. Stabilize and configure with approach flaps, they have to be set 1 nautical mile before the final approach fix according to SOPs. So, you must be at 1,500 feet, on speed and configured when overflying the final approach fix. Then the show is starting. When passing the final approach fix, use the magic 5 Gs. Gear, down. Glide, slope follow. Go timer, if needed. Go around, altitude set. Green lights, check gear and flaps lights. Talk, passing the final approach fix inbound or passing Victor Sierra inbound. Lot of work you say. Yes, but not finished. You have to talk, passing the final approach fix inbound or passing Victor Sierra inbound. And ATC will reply with contact Volocien info on 122.605. Then you switch frequency, call info stating your position and intentions, copy the traffic and the elements. You have to do that on top. Let's have a closer look at those steps. Gear, down, at the final approach fix as per SOPs. Glide, start the descent. At which rate? Check your ground speed. If you fly at 100 knots, you are asked a rate of descent of 531 feet per minute. Be as precise as possible, as on this approach, you have no other tool to control your vertical position. You can refer to the GPS waypoint Mike November 11, but, if you do not have GPS, if you adopt a steeper descent rate, you might be introduced with the planet Earth unexpectedly. Or a lower rate will not allow you to be at the minimas to see the runway. Go timer, why? Because you need to know when you are supposed to reach the missed approach point, M on the chart. And as you have no other mean than the timer, you have to start it at the right time. For how much time? Check the table. You see the NDB to MAP time, for 3.3 nautical miles, is, at a ground speed of 100 knots, 1 minute and 59 seconds. Be careful. As you see, you are flying this approach in CDFA. Which means continuous descent final approach. In this type of approach, you are not authorized to perform a level off. But you can adapt the rate of descent to reach your goal. If you reach the minimas too early, no level off, you must do a go around. Go around altitude, set on the altitude bug, is self-explanatory. Green lights. By the time you did all those steps, you should be able to check the 3 green lights of the landing gear and the flaps light or position. Of course, during the descent, you will have to announce the different checks. 1000 AGL for the approach band concept. 500 feet above the minimas for stabilization criterias and checklists done. 100 feet above minimas to start looking for visual references for landing. Be careful not to pull on the stick or the yoke by reflex. Minimas. If visual clues are found, announce, visual, continue. And proceed for landing. Follow the visual guidance if any, PAPI, VASI, and land. If no visual clue is found, then at minimas, call go around and proceed for the depicted procedure, except if you have received another clearance by the ATC. The approach ban, NCOOP.210, prohibits the continuation of an instrument approach below 1,000 feet when the reported RVR is below the operator's aerodrome operating minimum. It is intended to avoid an unacceptable rate of go-arounds when visual reference cannot be acquired and maintained at DH, MDH. To make it simple, an approach can always be started, whatever the weather conditions. At 1,000 feet AGL, you must have the minimum requirements to shoot the approach. Here, RVR of at least 1,500 meters for a straight-in landing CDFA, 2D. With a ceiling of at least 485 feet AGL. So, at 1000 feet AGL, grab the mic and just say RVR check and get the actual data. If above the minimums, then continue, if not, then go around. After passing the 1000 feet AGL where you had the required minimas, if they drop below the minimum required, you may continue the approach. Here, we have to make a distinction between MDA, H, and DA, H. DA, H, decision altitude, height. It's the altitude or height at which you make the decision either to continue for landing, or go around. Of course it takes a little time during which the aircraft continues the descent. In a go-around at the DA, H, you will continue to descend slightly below the DA, H, during the procedure. This is allowed because it is a decision altitude, height. MDA, H, minimum descent altitude, height. You are not allowed to descend below that altitude, height. Decision must be made before reaching that altitude, height, so you do not go below that floor. That is the reason why, on some airlines, they add some feet to the MDA, H, for the decision-making time, 50 feet, 30 feet, 0 feet. Adding some feet to the MDA, H, is the decision of the operator only, airline or you if you are flying as private, and here, he can also consider the minimum as ADA, H. Once a go-around is started, it cannot be stopped. Go-around. The go-around will be flown exactly as depicted on the approach chart. Climb on 097 degrees to 1,100 feet, then turn left, max 160 knots, to NDB climbing to 2,000 feet. Main things to remember when you are preparing the approach and do the briefing: refer to the briefing presentation, are first, and maybe second, direction and first, and maybe second, altitude. For example, here, 097 degrees, 1,100 feet, left NDB, 2,000 feet. Altimeter bugs will be set to 2,000 feet, which is the go-around altitude without level off. If there is a level off during the depicted procedure, altimeter bugs will be set to the first level off depicted to avoid any altitude bust. Remark: check that you cannot turn before passing the missed approach point, and you cannot accelerate before 1,300 feet. At this point, you have the choice to either restart the approach procedure, enter the holding to assess the situation and make a decision, or depart to your alternate.
Failures, irregularities and contingencies.
As a good pilot, you know that things are not always working as expected. So you are ready for as much as unexpected events as possible. Among those, what can you foresee? No talking about airport closure or aircraft technical defects such as engine failure or hydraulic failure, but only considering weather and/or navigation instruments.
Weather.
In this case, NDB, it is the least precise approach type. Your only option is to discontinue the approach and either proceed to enter a holding if you have fuel enough to wait for better weather conditions, or to go to an alternate with more friendly weather forecasts. Of course, as a good pilot, you already plan that, if you were to decide to divert, you would go to such airport that has such conditions according the destination alternate rules. For a diversion airport with only a 2D approach available, you plan your departure with, at the alternate estimated time of arrival ETA, a weather with 1,000 meters more than RVR or visibility required, and a ceiling 200 feet above the ceiling required. What can go wrong with my indications? Airport side. Failure of the antennas, system. Aircraft side. Failure of the instrument. Failure of the screen, AFIS. Be careful. In case of failure of your ADF, there will be no warning flag on the instrument. The needle will just stop moving, or will go in the 90 degrees park position. Some pilots like to listen to the IRREGULARITIES and trough out the approach. I consider that as useless as, after more or less 15 seconds without action after a stimulation in a high workload environment, The brain just disregards the alarm and you just don't hear it anymore. Moreover, that technique does not cover the onboard instrument failure, just the receiver. Failure of the antennas system. In that case, you don't receive any information from the system. NDB is inoperative, do not start the approach, or go around. Ask ATTC if another approach is available, one that you are equipped to fly of course. Failure of the instrument. You have no more indications on your PFD about your ADF positioning. Above 1000 feet AGL, you can reconfigure to another type of approach, reset your minimas, brief the approach differences and the descent profile. If you completed all your tasks before 1000 feet AGL, then you can continue the new approach, if not, go around. Do not forget that, now, you need new RVR minimas and sealing to be authorized to start the approach. Below 1000 feet AGL, go around and prepare for another type of approach. No real need to consider a diversion as the problem is coming from your equipment. Of course, if NDB is the only approach available, you have to change approach, or divert to another airport where you can use a different approach type. Failure of the screen, AFIS. On the G1000, you have an automatic changeover feature that switches your MFD to APFD and you recover all your information to be able to shoot your approach. You will still have a GPS map available through the inset feature. Keep in mind at all times. Error, unable to intercept and or track the inbound radial. The QDM to the station is difficult to hold and track as you are very close to the station. Do your best to overfly the station as close as possible to the QDM required. When switching from a QDM to a QDR, after overflying the station, it will be much more easy to track a QDR as you fly away from the station. Fixes. Make small changes. React to the needle tendencies, not movements. Use the rudder on small aircrafts, otherwise your aircraft is not turning, just slipping. Not more than 5 degrees correction in heading, 2 degrees correction in pitch at one time and give some time to the needle to react. Find a heading that holds the needle on target. The needle is lying to you. Know that there is the dip error in a turn, giving an error of about 10 to 15 degrees during the turn. Never make a decision during a turn, wait for the wings to be level and the needle stabilized.
Error, unable to hold the glide slope. Fixes.
You failed to get pitch stabilized on the approach. Use a predetermined power setting to pitch to a specific airspeed. Use trim to set your descent rate, about 500 feet per minute at 90 knots ground speed. Make small pitch adjustments, not more than 2 degrees at one time. Give time to the needle to react. React to needle tendencies, not movements.
Error, arriving at the final approach fix unprepared. Fixes.
Use next step concept to be set for the approach well before reaching the FAF. At the FAF, intercepting the glide slope, use the 5Gs concept. Gear, down. Glide, follow. Go timer, if needed for approach. Go around, altitude set on altitude bug. Green lights, gear and flaps lights checked. Fly the approach as if you are going to miss, review the first steps of the missed approach.
The 5 most common errors on the NDB.
Failure to understand the movements of the needle, QDM versus QDR. Failure to intercept and capture the QDM outside the FAF. Failure to establish stabilized power settings and trim for airspeed. Failure to maintain awareness of where you are before, during and after the approach if you miss. Failure to understand the approach, to properly brief it to yourself. If you can't explain what you are going to do, you can't fly it.